Imagine spending an entire year isolating a single priceless droplet of rare genetic material, and then you lose half of it and completely destroy your target cell in the process,
Right.
just because the microscopic glass needle you used decided to act like a clogged vacuum cleaner.
Oh, yeah, it's an absolute nightmare because operating at that scale, your target is inherently delicate. The fluid payload is, well, it's usually severely supply limited.
Right.
And your margin for physical error is basically zero. The tools we've relied on for decades they fundamentally clash with the precision of the biology we're trying to manipulate.
Exactly. And so when we talk about the ultimate final application dream in biomedicine, there's this persistent vision of absolute, uncompromising physical precision. We want flawlessly executed single-cell therapies. We want perfect in vitro fertilization.
Deep tissue interventions, too.
Yes, like direct-to-brain drug delivery, where you can navigate a payload to a specific millimeter of cortex. But to actually make that dream a reality, the physical engineering crashes headfirst into a really brutal biological reality. Delivering microscopic payloads into living targets without destroying them is, frankly, really hard.
It really is.
Well, welcome to this deep dive. Since you, our listener, are already an expert in two-photon lithography, we are definitely not going to waste your time explaining the physics of femtosecond lasers or, defining what a voxel is.
Right, we can skip the basics today.
Exactly. You already know this technology can print insanely small, beautiful, high-resolution structures. But our mission today is to pull 2PP out of the novelty prototyping lab and into the messy, high-stakes reality of actual biological engineering.
Which is such an exciting shift.
It really is. We are unpacking two highly impactful papers by Sarkar et al. There's one from Advanced Materials Technologies in 2023 and a brand new one from Microsystems and Nanoengineering in 2025. And these papers, they reveal how 2PP is stepping up to solve massive, scalable production bottlenecks for high aspect ratio, uncloggable microinjection needles.
And the shift in perspective here is really what makes this research so compelling. I mean, the 2PP community has historically been so captivated by the sheer geometric capability of the tech. We've all seen the microscopic castles and the tiny 3D ships printed on the head of a pin.
Oh, the classic benchy boat.
Exactly. But the Sarkar papers represent a real maturation of the field. We're looking at how those submicron geometric capabilities are being weaponized to solve severe fluidic and surgical bottlenecks that have plagued researchers for, gosh, the better part of a century.
Yeah, so let's tackle the manufacturing bottleneck first. We are looking specifically at microneedles. Now, you might remember we actually talked about this broad topic in a previous deep dive called 3D-Printed Microneedles Detect Food Allergies.
Oh, right. I remember that one.
Yeah. But today our focus is specifically on fluidic delivery, replacing the manual, archaic process of making glass capillary needles. I mean, the gold standard for decades has just been to take a glass tube, heat it up, pull it until it thins out into a microscopic thread, and then literally snap a tip to create an opening.
Which is wild when you think about it because the entire process is completely stochastic.
Right.
When you pull and snap glass, you get massive needle-to-needle variability. That outer diameter, the inner channel diameter, the angle of the break, it's all different every single time.
Which is a huge problem.
Huge. If your biological experiment requires delivering, say, an exact picoliter of fluid into an embryo, that geometric variability means your flow rate is changing with every single needle you make.
Wow.
And scaling that up to an array, like a high-density grid of microneedles to deliver payloads over a distributed area like brain tissue, it's functionally impossible using pulled glass.
Which brings us right to the classic 2PP scale bridging nightmare. As 2PP experts, you know the absolute pain of trying to print anything macroscopic.
Oh, it takes forever.
Literally an eternity. Scanning a tiny focal volume to build something large enough to actually interface with standard lab equipment like a macroscale fluidic input port. It's like trying to pave a multi-lane highway using a pair of tweezers.
That is a perfect analogy. It's just the wrong tool for bulk volume work.
Yeah. And in the past, researchers tried to solve this by printing just the microscopic needle tip with 2PP and then manually gluing it to a standard macrocapillary.
Right, and applying adhesives at that scale almost always leads to disaster.
Because it just seeps everywhere.
Exactly. You deal with capillary action, pulling the glue right into your microchannel, blocking it entirely before you even use it, or the alignment is slightly off, which creates a stress concentration that just snaps under pressure.
Yikes.
But the 2023 Sarkar paper introduces a total paradigm shift by just completely eliminating the adhesive.
Thank goodness.
Yeah, they utilize a hybrid additive manufacturing approach. They combine digital light processing, or DLP, with ex situ direct laser writing.
Ah, okay. So they let the DLP handle the bulk volume of the highway and save the 2 pp for the microscopic details.
Exactly. The DLP printer is used to rapidly batch print the microscale capillaries because, it's a vat photopolymerization method that cures entire layers simultaneously, so it can just churn out massive arrays of these larger input ports.
Makes sense.
And these ports feature custom interfaces designed to snap directly into existing commercial microinjector equipment.
Well, that's smart.
Yeah, so once that batch is finished, they take the DLP printed base, wash it, and load it straight into the 2pp system. This is where the ex situ direct laser writing comes in. They use the femtosecond laser to print the hollow microneedle arrays directly onto those pre-printed capillaries.
Wait, hold on. Let me stop you there because the alignment process for ex situ DLW is notoriously finicky.
It is.
If you have this macroscopic block of polymer sitting in your 2pp machine, how on earth does the laser find the exact microscopic center of that pre-printed macro capillary to build a needle on top of it? I mean, if it's off by even 10 microns, the fluid channel won't line up at all.
Right, alignment is critical. So the researchers rely on the optical feedback systems built into modern 2pp platforms. The system uses laser scattering or confocal detection to basically map the topography of the DLP printed substrate.
Okay.
It sweeps over the surface, locates the exact edges of the macrochannel opening, calculates the true center coordinate, and then anchors the 2pp print job precisely over that void.
Oh, wow. So it's actively finding the hole.
Exactly. But the real magic is what happens at the chemical level.
Because they aren't using glue, they're relying on their resins to bond to each other.
Yes. The DLP capillaries and the 2pp needles are printed using compatible photocurable materials. So when the 2pp laser begins printing the base of the microneedle ray, it's focusing its energy directly at the interface of that DLP structure.
Okay, I see where this is going.
The two-photon absorption process triggers polymerization that cross-links the new voxels directly into the unreacted polymer chains lingering on the surface of the DLP macrostructure.
So they are literally chemically fusing the two prints into a single monolithic part.
Precisely. It creates a seamlessly integrated, continuous fluidic path from the macroscopic input port all the way down to the microscopic needle tip. There's zero physical seam or adhesive layer to fail.
I mean, that sounds incredible. But I'm still a bit skeptical about the mechanical integrity of that hybrid joint.
Fair enough.
If I'm a biomedical engineer performing an injection, I have to push pressurized fluid through a tiny 30-micrometer hole at the tip of that needle array. The back pressure in that system is going to be immense.
Oh, absolutely.
So does that cross-linked resin joint actually hold up, or is it going to just delaminate and blow out the side the second I step on the foot pedal? I mean, is this just a delicate proof of concept?
The microfluidic cyclic burst pressure testing data in the paper puts that skepticism completely to rest. Yeah. They hooked these hybrid arrays up to a pressure system and subjected them to continuous pulsing. The seal effortlessly withstood input pressures in excess of 250 kilopascals for 100 consecutive cycles.
Over 250 kPa.
Yep.
That's roughly 2.5 atmospheres of pressure pushing through a sub-millimeter channel.
And they observed exactly zero fluidic leakage or compromised integrity at the hybrid interface.
Wow.
The chemical bonding between the ex situ DLW layer and the DLP substrate is incredibly robust. It really proves this isn't just a delicate desktop demonstration. It's a mechanically rugged, fully sealed system ready to handle highly pressurized biomedical payloads.
Okay, so we've solved the manufacturing bottleneck. We have this perfectly sealed, tightly packed, high aspect ratio array that seamlessly bridges the macro to the micro.
Exactly.
But structural integrity means nothing if the system fails biologically, because the second you take that beautiful geometric CAD model and shove it into living tissue, well, it clogs.
Yeah, the clogging crisis. And that is the primary focus of the 2025 Sarker paper, which scales the application down to singular needles used for embryo microinjections.
Right.
When you analyze a standard microinjection needle, whether it's pulled glass or even just a basic single-channel 3D printed cone, it has one opening located right at the apex of the tip.
Right at the point.
Exactly. And when you drive that tip through the chorion and into the yolk of a living embryo, that opening acts just like a microscopic cookie cutter.
Oh, it just cores the tissue. The physical force of insertion literally scoops the cytoplasmic material straight down into the tip of the needle.
Yes. The biological material wedges into the channel and completely obstructs the flow path. And this is what causes that wild, unpredictable variability in fluid delivery we talked about.
Because it's completely blocked.
Or partially blocked. On one injection, the clog might be partial, which reduces your flow rate. On the next injection, it might wedge so tightly that the needle is completely blocked, forcing the researcher to scrap the needle entirely, recalibrate the pressure system, and start over from scratch.
Now, I know someone listening is inevitably thinking, well, traditional cleanroom silicon micromachining can fabricate microneedles with side ports to avoid this exact coring problem.
And they wouldn't be wrong.
True. But traditional lithography is heavily labor-intensive, it is astronomically expensive, and it's fundamentally limited by 2D extrusion. You are constrained to these chunky, rectangular, planar motifs that have to be etched and bonded.
Right.
2PP completely ignores those constraints, offering true, arbitrary 3D submicron versatility.
And the Sarker team leveraged that exact 3D versatility to completely re-architect the geometry of the needle tip. They printed a monolithic high aspect ratio needle standing 650 micrometers tall with an incredibly thin 15 micrometer outer diameter and a 10 micrometer inner diameter.
That is so thin.
But the real genius of the design lies in 3 specific anti-clogging architectures that are really only possible with DLW.
Yeah, looking at the CAD renderings for this design, the first thing that jumped out at me wasn't the fluidic channel at all. It was the fact that the tip of the needle is entirely solid. They literally closed the top.
Exactly. They engineered an ultra-sharp, solid, fine point tip. When that solid spike hits the embryo, it doesn't core the tissue. It cleanly pierces and parts the tissue, displacing the biomaterial outward rather than scooping it inward.
But then to actually get the payload out of the needle, they printed multiple 5-micrometer side ports arrayed along the walls of the tip, positioned perpendicular to the insertion path.
Yep.
It reminds me of the difference between driving a snowplow with an open pipe on the front versus driving a torpedo.
Oh, that's a great way to picture it.
Right. The open pipe is going to fill with snow instantly no matter how fast you drive. But the torpedo shape displaces the dense environment as it moves forward, creating a slipstream. This 2PP design safely ejects its fluid payload laterally out of the side ports and into that wake.
And the fluid dynamics of that lateral ejection fundamentally altered the clogging risk. I mean, for the embryo's cytoplasm to clog this new design, the biological material would have to flow backward against the slipstream, take a 90-degree turn, and simultaneously wedge itself perfectly into multiple 5-micrometer side ports.
Which is absurd.
It is. It takes a process that was an absolute physical certainty coring and turns it into a mechanical improbability.
And the researchers didn't even stop at protecting the needle from the external environment. They printed an internal microfilter right at the base of the microchannel.
The filter is crucial.
They built a grid of pores measuring just 3.25 by 3.25 micrometers inside the needle itself.
Because biological payloads are rarely just pure homogeneous liquids, right? They contain suspended nanoparticles, dense protein structures, or delicate genetic aggregates.
A messy soup.
Exactly. If a microscopic clump in your expensive payload travels up the fluid path and wedges into that incredibly narrow 10-micrometer main channel, your needle is just as ruined as if it cored tissue from the outside. So the internal microfilter physically traps those aggregates at the wider base of the structure before they can ever enter and jam the microchannel.
When you zoom out and look at the biological implications of this geometry, it entirely bypasses a deeply frustrating historical trade-off.
It really does.
Previously, if your pulled glass needle kept clogging, your only real option was to snap it further up the taper to create a larger hole. But a larger hole vastly increases the physical trauma to the embryo. You solve the clogging problem, sure, but you basically explode the target cell.
Right. And by utilizing 2PP to physically separate the piercing mechanism from the fluid delivery mechanism, scientists can cheat that trade-off entirely.
That's brilliant.
The solid fine point tip provides the safety of an ultramicroscopic puncture wound, while the multiple side ports provide the combined, reliable fluid flow rate of a much larger opening.
Now, this all sounds mathematically and geometrically bulletproof on paper. But as we established earlier, biology is chaotic. Tissue is wildly heterogeneous. How do these intricate architectures actually perform in the ultimate in vivo test?
Well, the 2025 paper validates the design by performing high-throughput serial microinjections on live zebrafish embryos.
Okay, real living biology.
Yep. And this wasn't a cautious one-off proof of concept. They performed 100 serial injections per needle to track performance and degradation over time.
Wow. Let me guess the baseline control. The conventional glass-pulled needles struggled to maintain consistency.
To put it mildly, the glass needles failed predictably and stochastically. The researchers tracked the volume of fluid delivered into the yolk across the series. With glass, the delivered volume fluctuated wildly from one embryo to the next as microscopic tissue buildup altered the flow dynamic.
Right, because of the partial clogging.
Exactly. And on many attempts, the needle clogged completely, delivering absolutely zero fluid, rendering that specific injection a total failure.
And how did the 2PP printed 3D side port needles fare over the exact same 100 serial injections?
There were exactly 0 instances of complete blockage across all 100 injections. Zero. The volume of fluid delivered remained highly consistent from the first embryo all the way to the 100th. The solid tip and side ports completely neutralized the coring effect, avoiding the catastrophic failure seen with the glass baseline.
That's amazing.
And they even outperformed standard 3D printed control needles that lacked the side ports.
That level of reliability is just wild. And just to round out the biological validation, the 2023 paper tested their macro-micro mRNA arrays on excised mouse brain tissue.
Right, a much denser tissue environment.
Yeah, they needed to see if those tightly packed 50-micrometer wide needles could handle dense neural tissue. And they successfully penetrated the cortex, delivered their fluid and nanoparticle payload simultaneously across the distributed grid. And this is crucial, they retracted the entire array without the needle shafts snapping off and embedding themselves in the brain.
Which is huge. The successful retraction proves the sheer mechanical resilience of both the polymer itself and that hybrid DLP to ESDLW interface we discussed earlier. It easily survived the immense lateral shear forces exerted by dense biological tissue.
I do have to play the skeptic regarding throughput, though. Let's look at the reality of a fast-paced biology lab, or like a high-volume IVF clinic.
Okay.
A skilled technician can heat, pull, and snap a glass pipette in, what, 3 seconds?
Yeah, very fast.
According to the paper, it takes about 10 minutes to print a single 3D needle tip with these complex internal filters and side ports. Is a 10-minute fabrication time per needle actually practical in the real world? Are biologists really going to wait around for that print job?
It's a fair question, but the throughput equation changes drastically when you look beyond raw fabrication time and evaluate total experimental efficiency.
Oh, so?
Because pulled glass is stochastic, it ruins experiments. If you are injecting a rare, supply-limited CRISPR payload into an embryo, a clogged glass needle doesn't just cost you the 3 seconds it took to pull the glass.
Right.
It costs you the precious genetic payload that gets stuck in the clog, it costs you the biological target you just destroyed, and it costs you the hour you spent setting up the injection protocol.
Ah. So the actual cost of failure completely dwarfs the time saved on fabrication.
Absolutely. Furthermore, you have to consider calibration time. The conventional glass needles tested in the study had a mean outer diameter of 15.0 micrometers, but with a massive standard deviation of plus or minus 4.0 micrometers.
That's a huge variance at that scale.
Exactly. So every single time a biologist swaps in a new glass needle, they have to run a tedious calibration protocol to figure out its unique flow characteristics.
Oh, I see.
The 2PP needles, on the other hand, had a mean outer diameter of 15.3 micrometers, with a standard deviation of just plus or minus 0.1 micrometer.
Wow, so that is an order of magnitude more precise. It behaves identically every single time.
Yes. The extreme geometric precision eliminates the per-needle calibration step entirely. You load the needle, set your pressure parameters once, and just trust the physics.
That makes a lot of sense.
And as for that 10-minute print time, the hardware landscape for 2-photon lithography is accelerating incredibly fast. With dynamic optical tuning, adaptive voxel resolution, and the significantly faster galvo scanning speeds of the newest commercial systems, that print time is rapidly shrinking.
Right, so the 10-minute mark is really just a snapshot of the current hardware, not a hard physical limit of the geometry itself.
Exactly. The workflow is only going to get faster, while pulled glass is inherently capped by manual human dexterity.
That's a really great point. So to summarize what we've unpacked today, 2-photon lithography is definitively no longer just a party trick for printing microscopic oddities.
Definitely not.
By combining it with macro-scale techniques like DLP And utilizing sophisticated ex situ direct laser writing, 2PP engineers are creating incredibly reliable batch-scalable tools. They are stepping out of the clean room and actively solving massive, deeply frustrating bottlenecks in biomedical engineering. They are giving us uncloggable, geometrically brilliant fluidic tools that protect both the payload and the biological patient.
It's transformative. And as we look to the future, there is a really fascinating thread to pull here.
Oh, what's that?
Right now, the Sarker papers demonstrate using 2PP to print static mechanical solutions, right? Solid tips, static microfilters, stationary side ports.
Yeah.
But the technology's ability to seamlessly integrate complex internal features on the fly opens the door for dynamic architectures. Imagine using two-photon lithography to print microneedles with integrated mechanical microsensors or even fluidic logic gates built directly into the capillary walls.
Wait, you mean basically transforming a static delivery tube into a smart, responsive robotic appendage?
Exactly. A needle that physically feels the density of the cellular environment, autonomously assesses the internal pressure of the embryo in real time, and uses integrated fluidic logic to decide exactly how much payload to inject, adapting to the tissue dynamically.
Wow. Which brings us right back to the ultimate dream we started with. Perfectly precise, uncompromising, automated biological intervention.
It's the future.
Definitely something to mull over the next time you're staring at your CAD software, trying to figure out how to scale up your voxels.
Yeah.
Thanks for joining us on this deep dive.